Assalamu alaikum. This video I am recording to demonstrate the working of active fault tolerant controller, which I have designed to control the quadcopter in the presence of actuator faults. This is my simulation based model where the quadcopter, actuator faults and active fault tolerant controller, all of these blocks are in Simulink or the simulation environment. If I explain little bit about active fault tolerant controller, active fault tolerant controller consists of two subcontrollers. First controller is the integral backstepping controller. Integral backstepping controller is used to control the translation motion of quadcopter. Second controller is the sliding mode controller. Sliding mode controller is used to control the rotational motion of quadcopter. Design of sliding mode controller is based on nonlinear disturbance observer. Nonlinear disturbance observer is used to estimate the faults or the disturbances present on the quadcopter. So this is the brief about active fault tolerant controller. So to test this model in the hardware in the loop configuration, I have generated the Verilog code for active fault tolerant controller block and then synthesized the Verilog code using Xilinx Vivado software and then generated the bitstream file for this active fault tolerant controller. Now this is my second file where I have replaced this active fault tolerant controller block with its equivalent FPGA block. This block is now representing the actual FPGA board which is connected with my laptop. So rest of the model is same. Now in this file my active fault tolerant controller will be running on FPGA while quadcopter and the actuator faults will be in simulation environment. So this is my setup to perform the hardware in the loop implementation testing. So now I can upload my bitstream file into the FPGA. My FPGA board is connected but it is not yet programmed. So here is my bitstream file for my active fault tolerant controller. So now I can apply this, and now if I load this these LEDs which are blinking now will be stopped, and furthermore I will also got the message on screen. You can see that I am getting the message loading FPGA programming file. I have obtained the message that FPGA programming file loaded successfully. It means that my active fault tolerant controller is now successfully implemented on FPGA board. Furthermore, the LEDs which were blinking on the board are now turned off, indicating that the program is or the bitstream file is successfully uploaded. Now I can perform hardware in the loop implementation. So here is my fault vector and this is my time at which I can apply this fault vector, and here I can select the motor number at which motor I want to apply the fault. Let's set this to be 1. So it means that I am applying the fault at motor 1, 10% fault at the time of 15 seconds, and 20% fault at the time of 35 seconds, and so on. And at the time of 95 seconds I will be applying the fault of 50% more, 50% partial failure on motor 1. Now we can perform the hardware in the loop implementation. You can see that my system is now in running condition. Here this is the hardware in the loop in action. Now my controller is running on FPGA board while my quadcopter and my actuator faults are in simulation environment. This is the setup for hardware in the loop implementation. So the simulation or the hardware in the loop implementation running is completed. Now we can observe the hardware in the loop implementation results. These are my trajectories, actual trajectories and reference trajectories. You can observe that the actual trajectories and the reference trajectories are equal. So the quadcopter is tracing the actual reference trajectories in the presence of fault. Here is the output of the nonlinear disturbance observer. You can see that the disturbance estimated by the nonlinear disturbance observer. As the magnitude of the fault is increasing on motor 1, the estimate of the disturbance provided by the nonlinear disturbance observer is also increasing. Furthermore, if I show the speed of the propellers, these are my speed graphs. You can observe that I have applied the fault on motor 1, which is gradually increasing from 10% to 50%. Accordingly, the speed of motor 1 is gradually decreasing. If I zoom it a little bit, you can observe that now as the fault is increasing on motor 1, the speed of motor 1 is increasing. Similarly, if I show you the speed of remaining 3 motors, they are going to increase. So fault is injected on motor 1, so its speed is decreases, while to compensate the partial loss of the effectiveness of motor 1, the speed of remaining 3 motors is going to be increased, and which we can verify from the graphs. So now let me show you the control variables. These are my control variables. The first variable UF1 represents the thrust, while the remaining 3 variables UF2, UF3 and UF4 represents the torques or the moments. Let me show you that the effect of the fault is neglected by our system. You can see that at the event of fault on the system, momentarily the thrust vector decreases, but immediately it recovers to its steady state value, cancelling the effect of disturbance, while similarly the rotational movements or the torques are accordingly changed. Here is main is the thrust vector. It is clearly showing that the effect of disturbance or the partial failure of motor 1 is clearly rejected by the active fault tolerant controller. So now let me apply the fault on motor 2. Again I can run the simulation. Now these faults are injected on motor number 2, the fault value is increasing from 10% to 50%. Now this is hardware in the loop. System is running and the fault is injected on motor 2. In this configuration, my controller is working on FPGA board while my quadcopter model and the actuator faults are in simulation environment. So the simulation is just completed for 120 seconds. We can again observe that our actual trajectories are tracking the reference trajectories. Similarly, now we can see the effect of speed. Now you can observe that as I have applied the fault on motor 2, now the speed of fault motor 2 is continuously decreasing due to the increase of fault, while the speed of the remaining 3 motors, motor 1, motor 3 and motor 4, is increasing little bit to compensate for the fault on motor 1. Similarly, we can verify that on motor 3 and motor 4. Let me quickly show this. Now the fault is injected on motor 3 and the hardware in the loop implementation is in action. Now just let me show you first of all trajectories which are as usual stable, that is fault effect is not present on the reference tracking of reference trajectories. Similarly, if I show you the speed curves for each of the motor, now I have applied the fault on motor 3. So the speed of motor 3 is continuously decreasing due to the increasing fault, while the speed of the remaining 3 motors is going to be increased. Now let's just test or apply the fault on motor number 4. And quickly re-simulate the whole system. This is my complete setup. FPGA board is connected with my laptop. My active fault tolerant controller is running on FPGA board, while my quadcopter and actuator faults I am applying in the Simulink environment. So let me show you the graphs again. The system is tracking the reference trajectories. Now let me show you the motor speeds. As the fault was injected on motor number 4, so the speed of motor number 4 is going to be decreased. So it means that motor number 4 is losing its effectiveness, while the speed of the remaining 3 motors will increase to compensate the effect of the fault on the system. And finally, let me show you the estimate of the disturbance provided by the nonlinear disturbance observer. So from here we can verify that our system is in running condition even in the events of the fault on the system. So in this video I have demonstrated that active fault tolerant controller is working successfully on FPGA board in the hardware in the loop implementation, and it is in this I have demonstrated that I have varied the fault on the system on each of the motor from 0% to 50%, and for each of the case the fault tolerant controller is giving the stable system response, and if cancelling the effect of faults on the system and providing the stable trajectory response. Allah Hafiz.